Hello students, in today's session we will discuss a very important topic and interesting one too. We will start with dimensional analysis. As we are all aware, there are two types of units. One are basic or fundamental units, the other one are the derived units. Derived units, you must remember, these are those units which can be expressed in terms of basic units, right? And in SI there are 7 basic units, we all are aware of it. So basically the dimensions of a physical quantity are the powers to which the fundamental units of mass, length and time have to be raised so as to obtain the unit of that physical quantity. I will elaborate with an example first. Suppose we consider the case of force. Its formula is mass into acceleration, right? So, SI unit of mass is kg, SI unit of acceleration is meter per second square. So, it will become kg meter per second square and SI unit is Newton. Now look, the dimension formula for force will be written in this particular manner. Kg, it represents mass. Meter, it represents length. Second, it represents time. Now, force is dependent on mass as kg to the power 1. So, the dimension of force with respect to mass is 1, like this. It is 1. It depends on length, that is meter. Dimension of length is 1. Dimension of time is -2. So M represents the mass, L represents the length and T represents the time. So this will be the dimensional formula of force. So let me state the definition. The dimensions of a physical quantity are the powers to which the fundamental units of mass, length and time have to be raised so as to obtain the unit. Right? Let's again take some other example. Suppose speed, it's equal to distance over time. Now distance, it's measured in meter, time it's measured in second, so it will be meter per second. So the dimensional formula for the speed would be m. It is not depending on mass, it is independent of mass. That is, its dimension in mass is 0. M represents mass, so raised to power 0. Its dimension in length is 1. Its dimension in time is -1. So this is it. So its dimensional formula is m to the power 0, L to the power 1, T to the power -1. Obviously, anything to the power 0 is 1. Anything to the power 1 would be the same thing, right? So it can also be written in this particular manner. L T -1. So again, I am repeating the definition. The dimensions of a physical quantity, which in this case are considered to be the velocity. The dimensions of a physical quantity are the powers to which the fundamental units of mass, length and time have to be raised so as to obtain the unit. So this is how the dimensions of a physical quantity may be defined. Now in the next few minutes, what we will do is, we will try out different physical quantities and we will try to find its dimensional formula along with its SI unit, right? And students, we will discuss only those physical quantities which you are already aware of, right? We will restrict ourselves to only those quantities which you have already studied. So let's complete this chart. So let's start with length, mass, time. You all are aware. Suppose area, physical quantity is area. Formula is length into breadth or length into length. So it will be meter into meter, meter square. So dimensional formula would be M0, L2, T0. This will be the dimensional formula. Or simply you can write like this as well, like this. SI unit is meter square. Right? So the dimensions of area in mass is 0. The dimensions of area in length is 2. And the dimensions of area in time is 0. So this is the dimensional formula for area. SI unit is meter square. We all are aware of it. Similarly, volume. Its length into breadth into height. Right? For different geometrical figures, the volume is different. But actually the dimensions will remain same. So it's length, breadth, height. So meter into meter into meter. So SI unit will become meter cube. So it is dependent only on length. And the dimensions of volume in length is 3. So it can be written as m to the power 0, L to the power 3, T to the power 0. Or it may be written as L to the power 3. So the dimensions of volume in length is 3. Understood now? We have started with a very, very basic thing. Third, speed. Just now we have discussed. The formula for speed is path length divided by time. That is, it is distance divided by time. So what do you get? Meter per second. It is meter per second. So dimensional formula would be M0, it is independent of mass, L1, T to the power minus 1. Look, this represents the length, meter. This represents the time. So the dimensions of speed in length is 1 and in time is minus 1. That is what I have written over here. Or it may be written as LT minus 1. Right? From now onwards, I will be writing like this. Anything to the power 0 is 1. So it won't be mandatory for you to write that. Right? Anything to the power 0 is 1. So you can avoid writing this term. Fourth, acceleration. It is time rate change in the velocity. So that is change in velocity divided by time. So what we get is velocity, it's meter per second divided by second. So we get meter per second square, isn't it? So dimensional formula would be L T to the power minus 2. It is independent of mass. Understood? These are the quantities which we all are aware of. Fifth, just like we have discussed, force. It is mass into acceleration. SI unit is Newton. And 1 Newton is kg, mass is kg, acceleration is meter per second square. So from this basic units, you can easily write the dimensional formula. So it will be m to the power 1, it can be written only as m, L to the power 1, that can be written only as L, T to the power minus 2. So this is the dimensional formula for force. Right? Next, suppose work or energy. The SI unit is joule and its formula is force multiplied by displacement along the direction of the force applied. Then only this formula is valid. So F into displacement. Only when the body moves along the direction of the force applied. So it is Newton meter. Joule is Newton meter. Newton is this multiplied by meter. So what do you get? Kg meter square per second square. Right? We are aware of the unit of force in terms of the basic units. So force multiplied by meter. That is what I have done. So its dimensional formula would be m L2 T minus 2. So the dimensions of work in mass is 1, in length is 2 and in time is minus 2. Right? Seventh, pressure. This is the term which you are aware of. It is force per unit area. Now look, its SI unit is Pascal. And it can be written as SI unit of force is Newton, area is meter square. So Pascal is Newton per meter square. Now look, in order to get its dimensional formula, over here, pressure is force per unit area. Right? Force, it is kg meter per second square, mass into acceleration. Area, it is meter square. What do you get? Kg It will be n to the power minus 1, s to the power minus 2. Isn't it? Very simple. So, what will be the dimensional formula? M L to the power minus 1, then T to the power minus 2. This is the dimensional formula for pressure, right? A gravitational constant. Okay, what about its formula? Students, do you remember this formula? F equals to G m1 m2 divided by r square. So G would be equal to F r square divided by m1 into m2. This is the formula. So F r square divided by m1 into m2. Let us get its unit. Force, it is Newton. Distance square, it will be meter square. Mass into mass, kg into kg, that is kg square. Now we need to convert Newton in terms of mass, length, time, in terms of the basic units, right? So Newton, we are aware, Newton, this is Newton, is kg meter per second square. So Newton is kg meter per second square, mass into acceleration. Again, meter square divided by kg square. So what do we get? Kg inverse m to the power 3 s to the power minus 2. So that's it. So its SI unit is per kg meter cube per second square. Right? This is how you can derive or you can obtain the dimensional formula along with its SI unit. So what will be the dimensional formula for capital G? It's very important. It will be frequently used in the coming sessions. So it will be m to the power minus 1, m represents length, L to the power 3, S second represents time, T to the power minus 2. So that's the dimensional formula for gravitational constant. There are some other very important physical quantities as well, which we will try to discuss. So, angle. Formula for angle is length of the arc divided by radius. What is its SI unit? It is radian. Now look, length it's measured in meter, radius it's also measured in meter. So they'll get cancelled out. So its dimension in mass, length or time is 0. It is neither dependent on mass nor on time nor on length. So its dimensional formula is m to the power 0, L to the power 0, T to the power 0. Or simply you can write 1. Simply you can write 1. That is, it is dimensionless. It is a dimensionless quantity. So what we have concluded is, if a physical quantity is given by the ratio of two similar physical quantities, then that quantity must be a dimensionless quantity. Like, I'll give you another example. Refractive index. I'm sure you have done it in your junior classes. Refractive index is velocity of light in air divided by velocity of light in medium. Look, it is the ratio of two similar physical quantities. So, it do not possess any unit and it is a dimensionless quantity. It is a dimensionless quantity. Right? So, the point to be noted down is, whenever a physical quantity is given by the ratio of two similar physical quantities, then it must be a dimensionless quantity. Dimensionless means those physical quantities which do not possess any dimensions. Right? Okay. Next, power. I am talking about electric power, right? Not the power of lens. I am talking about electric power. Okay, let me write it over here. Electric power. Power is rate of doing work. That is, formula is work done divided by time taken. This is the formula for power. So joule per second. SI unit of work is joule, time any second. Joule per second is known as watt. It is represented by capital letter W. It is joule per second, right? Represented as watt. Now work done. Its dimensional formula is known to us. Divided by time, second. So students, its dimensional formula would be mL2 t to the power minus 3. Look, dimensional formula for work is mL2 t to the power minus 2 divided by time, that is t. So we'll get mL to the power 2 t to the power minus 3. So that's the dimensional formula for power, right? 12th, power of a lens. Power of a lens. It is given by reciprocal of focal length in meters. The formula is reciprocal of focal length in meters. Focal length, its SI unit is meter. So reciprocal of meter would be meter inverse. That is also known as diopter. Represented by capital letter D, diopter. That gives the power of a lens, right? So meter inverse. So it will be L minus 1. The dimensions of power of a lens in length is minus 1. I hope you are able to understand this. Any physical quantity, if the formula is known to us, then we can easily determine the dimensional formula by using this, right? Let's start with some other physical quantities as well, right? Like current, electric current. As you are aware, it's a basic quantity. It's a basic quantity. It's a basic unit is ampere. So this is the dimensional formula for electric current. This is the dimensional formula for electric current, right? You can't change it. Basic units are those units which cannot be resolved any further, right? And these are the basic units, electric current. So it will be written like this. This is the dimensional formula. Or you can write m to the power 0, L to the power 0, T to the power 0 and T. So this is also correct and this is also correct. It's your choice. So electric current, its dimensional formula is A. So students, can you give me the dimensional formula of charge? Find out the dimensional formula for charge. Charge is Q is equal to IT, current multiplied by time. Its SI unit is coulomb. So you can try it. Then in class 10, in the chapter electricity, you have discussed various terms, isn't it? Potential difference, resistance, resistivity, conductance, conductivity. So let's try to find out the dimensions of all those physical quantities. So only thing is, you should be aware of the formulas to be used. Knowing down the formulas, we can easily determine the dimension formula for any given physical quantity. So let's start. So what we have discussed is current, not charge, electric charge. What about its SI unit? It is coulomb. We are aware of this formula. Current is rate of flow of charge. So charge would be equal to I multiplied by T. So coulomb is ampere second. So dimensional formula for the charge is represented by Q. It will be equal to T. T represents second, time, and ampere, like this. TA. The dimensions of charge in time is 1. The dimension of charge in ampere is 1. Right? So let's proceed further. Let's find out the dimensional formula for resistance. Okay, what's the formula for the resistance? R is equal to V by I, isn't it? This is Ohm's law. And before finding the dimensional formula for resistance, we need to find out the dimensional formula for potential difference. Potential difference is V. It is work done per unit charge. So let's find out the dimensional formula for potential first, and thereafter we can find out the dimensional formula for resistance. So let's do it. So students, the SI unit of potential difference is volt. Right? It is represented by capital letter V. And it is work done per unit charge. Remember, work done per unit charge. Work done, its dimensional formula is kg meter square per second square, right? Charge, just now we have discussed, it's ampere second. Q equals to IT, it's ampere second. So what will be the dimensional formula for potential difference? It will be M L2 T to the power minus 3 and A to the power minus 1. So this is the dimensional formula of potential difference or electric potential, right? Now knowing the dimensional formula for potential difference, we can easily find out the dimensional formula for resistance. Look, it is V by I. V is this divided by I is ampere. So its dimensional formula would be ML2 T to the power minus 3 A to the power minus 1 divided by A. Potential difference divided by current, right? This is the dimensional formula for potential difference divided by current, that is ampere. So we'll get A to the power minus 2. This is the dimensional formula for resistance, and its SI unit is ohm, represented by this particular symbol, ohm, right? You must have done it in class 10 in the unit electricity. 16. What about resistivity? Resistivity. Now look, formula for resistance is R equals to rho L by A, and this rho, it is known as specific resistance or resistivity. So rho is equal to RA by L. Now look, resistance, it's ohm, area, it's meter square, length, it's meter. So SI unit is ohm meter. So SI unit of resistivity is ohm meter. And what about its formula? It is RA by L. What about its dimensional formula? Let's check it. Ohm, it can be written as ML2T minus 3A minus 2 multiplied by meter. Meter represents length. So what do you get? ML3T minus 3A minus 2. Right? So this is the dimensional formula for resistivity. Students, you need to know the formulas, right? And obviously the units of the numerical quantities which you are using in that particular formula, right? So its dimensional formula would be ML3T minus 3A to the power minus 2. What about conductivity? Now look, conductivity is reciprocal of resistivity. Conductivity is reciprocal of resistivity. They are antonyms. So it will be L by RA. Now since conductivity is reciprocal of resistivity, therefore the dimensional formula for conductivity would be inverse of the dimensional formula for resistivity. So it would be inverse of this, m to the power minus 1, L to the power minus 3, T to the power 3, A to the power 2. Right? What about the SI unit? Here it is ohm meter. Inverse of ohm is ohm inverse like this and meter inverse. This is the dimensional formula for conductivity. Let's proceed further. Specific gravity. This you must have done in class 9th, specific gravity or relative density. So, specific gravity or relative density. It is defined as density of the substance divided by density of water at 4 degrees Celsius. So again students, look, this being the ratio of two similar physical quantities, numerator density and denominator is also density. So it will be a dimensionless quantity having no unit. So no unit over here, and it must be a dimensionless quantity. It is a dimensionless quantity, right? Let's proceed further. Let's consider the case of solar constant. This is the term which you have studied in class 10 in the chapter energy. Solar constant basically is the amount of energy which is received by a perfectly black body placed on the Earth's surface in a direction normal to it per second per unit area. So what I have stated is solar constant is energy received by a body per second per unit area from the sun, per second per unit area. So even if you are able to understand the concept or you have a theoretical knowledge of that physical quantity, then also you will be able to find out the dimensional formula, right? So solar constant is basically energy received per second per unit area, that is per unit time and area. So using this formula we can easily determine its dimensional form. So it is energy received per unit time per unit area. Now look, SI unit of energy is joule, time is second, area is meter square, right? Joule can be written as in fundamental units kg meter square per second square, and over here second meter square. So you can modify it. Meter square get cancelled, we'll be left with kg s to the power minus 3. So the dimensional formula for solar constant would be m t to the power minus 3. This is the dimensional formula for solar constant. And what about its SI unit? It is joule per second per meter square. Joule per second is watt, so it can be written as watt per meter square as well, right? So it is watt per meter square. Clear? There are several other terms as well. So let's discuss 20th physical quantity. So here we can discuss stress. Obviously, I am not talking about mental stress. Stress is a physical quantity which we will be discussing. So stress is basically, the formula is force per unit area. So force is Newton, area is meter square. So SI unit would be Newton per meter square, right? Dimensional formula, force is kg meter per second square in terms of basic units, area is meter square. So what do you get? M meter divided by meter square will be left with m to the power minus 1, that is L to the power minus 1, T to the power minus 2. This is the dimensional formula for stress. So students, this was just to give you an idea. There are various other physical quantities as well. Now it's your turn to continue with this chart. Whenever actually you encounter a new physical quantity, just do add up that physical quantity in this particular chart. Keep adding the physical quantities, right? In that way, you will practice and you will come to know about the dimensional formula for various physical quantities which we make use of in physics. So students, that's it for today's lecture. I hope you have understood it completely. So what we have done today was the formula, dimensional formula, what are the dimensions of a physical quantity and how to write the dimensions of a physical quantity. We have discussed about 20 physical quantities, right? Okay, we'll continue in the next session then.